So we've made it to the final section of Chapter 1, 1.6, and we're going to talk about inverse functions. And so what we talk about here applies to a lot of the functions that we've already seen. However, all of them do not exhibit this property that we call one-to-one. And so it's not enough to be a function. It also has to be one-to-one, and if that's the case, then we can say that that particular function has an inverse function that pretty much just maps the y back to a particular x. Okay, and as with anything in mathematics, it's a lot easier to show you than to tell you. So we will get started with the examples. And so we have, much like we started out with talking about functions, we're going to start out with arrow diagrams. And all of these arrow diagrams, except for this one, are functions. So this one is a function. And so is this one. Okay, so let's just point out as to why these two are functions and this one's not. Well, notice that all of the inputs in our domain map to only one output. This dot, one arrow, this dot, one arrow, and the last one, one. And the same applies to this particular function on the right. This arrow diagram represents a relation instead, not a function, because of this input value. It tracks over to two outputs in this range. So this one on the bottom, it is not a function, so we cannot call this a one-to-one function. Alright, so we know which ones are functions. Which ones are one-to-one? Okay, well, even though this isn't a function, it is still one-to-one, because if now we take the outputs and trace them back to their original inputs, like so, we see that each output has only one input. Okay, so the inverse of this relation actually is a function, even though this is not a one-to-one function from D to R. Okay. This arrow diagram at the top is a function, however it is not one-to-one. If we trace this output back to its inputs, we get, maybe I should do this in a different color. For this one output, if we trace it back to the inputs, we get two inputs for this one output. So if I inversed these relationships, it would not be one-to-one. This middle range goes to 2. It's sort of like the same definition for a function, except in reverse. Okay, and this one on the right is a function, and it's one-to-one. So we could also say this is a one-to-one function, because if we look at the outputs and we map them back to their inputs, then each output only has one arrow leading away from it. Okay, so this is 1 to 1. Okay, so this leads us to B, and we have an algebraic expression for our f of x, and the question is this 1 to 1? Well, x squared plus 1 is a function, but it is not 1 to 1. So no. Okay, and it has to do with this x squared part. So let's just take a look at the base function. Y equals x squared. Okay, it would start at the origin. Okay, and if I take one of the inputs, or I'm sorry, one of the outputs, and map it back to the inputs. For instance, if I choose, let's say, y equals 4. Okay, well, what would give me an output of y equals 4? Okay, we could draw a horizontal line out from y equals 4, and whenever we hit the curve, we trace our way back down to the x-axis, and you see we hit in 2 points. That is because if I plug in a 2 or a negative 2, I get 4. So this output has 2 inputs. It is not 1 to 1. Okay, and the same idea applies to x squared plus 1. So say for instance I take this f of x and I put in a negative 2. This expression tells me to square negative 2 and add 1, and so I would get 4 plus 1 equals 5. Well, if I calculate f of positive 2, I will get 2 squared plus 1 equals 4 again, then add 1 and I get the same output. And so if I reversed the relationship and mapped the output to the input, I would have 5 traced back to 2 inputs. Okay, so this is not a one-to-one function for that reason. So let's look at C. Okay, well, is f a function? Okay, we already know how to check this. We simply check the first element of each ordered pair, and we ask ourselves, do they repeat? 2, 3, negative 1, 4, 0, and negative 2. No repeating inputs. So for a function expressed through ordered pairs, this tells us that well, it is a function. Okay, so now that we know it's a function, is it one to one? Well, we simply look at the outputs. Do they repeat? Okay, we have 1, 0, 5, 7, 2, and 3. Okay, so we have no repeating outputs, therefore it is 1 to 1. Okay, we stick the two together and say it's a one-to-one function. Okay. We can apply the same reasoning to G. We have 3, 2, 0, 7, 1 for the inputs. None of them repeat, so this is a function. Okay. Is it 1 to 1? Look at the outputs. We have -2, 1, and then -2 again. So in other words, we have an output, -2, and if we reverse the mapping, it gets mapped to two different inputs, 3 as well as 0. Okay, so we say this is not 1, 2, 1. Okay. Page 37, we're posed with a question. How can we determine that a function given by its graph is one-to-one function? The answer is given by the horizontal line test. So we have the vertical line test, which establishes whether a particular graph represents a function or not. And now we have the horizontal line test that tells us whether a particular function is one-to-one. Okay. So we've seen this one before, and if you'll look back in the previous sections, you should see that this is a function. This is not a function, because if I draw a vertical line along here, or anywhere else for that matter, I strike the curve more than once. Okay, so it's not a function. This curve passes the horizontal line test. There is no place along the x-axis where I can draw a vertical line and hit this curve twice. So this is a function. This one we haven't seen before, but it is a function. And so is this one. And then now we have this rational function, and keep in mind these dashed lines are vertical and horizontal asymptote. So horizontal asymptote, and then we have a vertical one, and so the curve of this relation does not cross these boundaries. Okay, and if I go through here and imagine a vertical line at various places, then I'm only going to hit the curve once. The only questionable place are these areas here that are close to the vertical asymptotes, and I'll just simply have to say that the x coordinates or the y, they are changing. They're changing such that if we were to precisely draw a vertical line through there, we would not hit it twice. Okay, so in other words, this is a function. But which ones are one-to-one? Very simple. Now I just simply use a horizontal line test with the same rule as I had for the vertical line test. Here's a function, and it's easy to spot a location along the y-axis where I hit the function more than once. Okay, so we would say this is not 1, 2, 1, not 1-to-1. Okay, now this is not a function, so we can call this a relation. And if I were to construct the inverse of this relation, then it would be a function. Okay, because this relation, it's not a one-to-one function, but this relation is one-to-one. There is no place along the y-axis where I can draw a horizontal line and strike this curve more than once. Okay, what about this function? Well, it looks like it flattens out through here, but it's probably still has a slight slope to it. If I imagine drawing horizontal lines at various locations along the y-axis, any place along here, I only hit it once. Okay, and around here you may draw a horizontal line and it looks like it strikes this area twice, but it will not in actuality. Okay, and of course this area of the y-axis is not in the range, and so we don't hit the function or the curve at all. So this one is 1, 2, 1. Okay, and so we'll simply run through the rest of these. This one is pretty obvious. Okay, just draw a few horizontal lines through here, and each of the ones that I've drawn are only hitting the curve once. So this one is 1, 2, 1. And here's another function, but there are several places where I can show that it is not one-to-one, and it only takes one y-coordinate to rule it out. One y-coordinate that has several inputs. Okay, so this is not 1, 2, 1. Alright, and this leads us to our last one, a rational function. And so if instead we draw horizontal lines for the horizontal line test, the only place where it looks like we might hit the function several times is right along through here. Okay, near the horizontal asymptote. All other places definitely pass the test. But I guess in this case I just simply have to tell you that this curve is at every instance of x. It gets closer. Well, in this case, if I go from right to left, this curve is getting closer and closer and closer with every change in x to the horizontal asymptote, and so the y variable is changing. Okay, likewise for this right side, as x increases, the y coordinate gets closer and closer to this horizontal asymptote. It'll never cross it. It will just continually get closer to it to infinity. Okay, so these areas will pass the horizontal line test, and so we can say this function is 1, 2, 1. Okay, so just to run back through them, this is not a one-to-one function, but it is a function. This is a relation, and if we were to create its inverse, then the inverse would be a function. This is a one-to-one function, this one on the right here. This one is a one-to-one function. This is a function, but it's not one-to-one. And the last one is also a one-to-one function. Okay. Alright, so let's do a little bit of reading here. All functions increasing or decreasing over the real number line, okay, are one-to-one. So if it's only increasing or if it's only decreasing, over the entire number line, it only exhibits one of these behaviors, then it's 1 to 1. And then it tells us that all linear functions are 1 to 1. Okay. So it says use the horizontal line test to determine which of the functions below are 1 to 1. Well, here f of x is linear. So according to theorem 1, this is 1 to 1. Alright, but we can still look at the graph. Okay, and we can't see the whole thing, but we've already talked about linear functions. And we decided that they are either constantly increasing or decreasing. In this case, negative 3x plus 7 has a negative slope. Okay, the slope is negative 3. So this one is always decreasing. Okay, the decreasing interval is from negative infinity to positive infinity. Graph. Okay, so we verified that it does have a negative slope, and this line just continues to travel up and to the left and down and to the right. Okay, it will never cut back onto itself with respect to the y-axis. Okay, so let's graph some of these other ones. G of x, the next one, is the square root of 2x minus 1, and there we have it. Okay, so there are some values that are not in a domain. Okay, we see that it simply starts here and then travels upward. And so what's happening here is as we put in a bigger x value, we get back a bigger y value. It looks like this curve flattens out, and it does to an extent, but it is always increasing. The increasing interval is from negative, well, not negative infinity, I'm sorry, is from 1/2 to infinity. Across its entire domain, it's increasing. So g of x is 1 to 1. Okay. We will clear out the square root function g, and let's put in this rational function h. I will put the denominator in parentheses so that it knows both the x and the minus 1 are in the denominator, and I'll graph it. Okay, this is one of those rational functions as we saw on the previous page, and this calculator does not insert dashed lines or the horizontal asymptote, but we definitely have a horizontal asymptote through, well, let's see, it looks like it may be through x or y equal 1. Not really sure, but as we stated before, this rational function is 1 to 1. Okay. The only questionable place is here along the horizontal asymptote. We don't cross the horizontal asymptote in between, and so we will not ever cross as we approach positive infinity and negative infinity. So we will not have a y coordinate that has two different inputs. Okay, and I also drew in here the vertical asymptote. H of x is 1, 2, 1 to 1. Okay, so I'm going to clear my screen, move my calculator over so I can graph these other two. What about k of x? Okay, again I have a rational function. I want x plus 1 in the numerator, enclosed in parentheses. Then I'll hit my division symbol, and enclose x squared minus 4 in parentheses, and graph. Okay, so not all rational functions, which this is a function, for every one output we get one input, it maps to one output. But two inputs could map to the same output, and that's exactly what happens if we apply the horizontal line test here. We say that we intersect k of x twice. So this is not 1, 2, 1. And finally, we will plot this parabola here. We have x squared minus 4x plus 3. Okay, and like any other parabola, it either opens up like a U or opens downward like an N, but this curve fails the horizontal line test. Okay, drawing a horizontal line anywhere above this x-axis results in 2 hits. Okay, and that only has to happen in one place in order to fail the one-to-one test, and so R is not 1, 2, 1. Okay, so all of these were functions. The first 3 were 1 to 1, and the last 2 were not. They failed the horizontal line test. The last 2. So if we look below at F, G, and then we have G again, what the remark is telling us is that F is our function. We can see that each input is only mapped to one output, x2 to y2, x3 to y2. Even though the middle two are mapped to the same output, they each separately only have one output, or one arrow leading away from them. Okay, so this is a function, and we can take the converse of that function, and we're simply calling that G. G is the converse of F. Okay, and you can see this should be y1, and here's y2 and y3, and we've simply reversed the arrows. Okay, but you should notice that y2 maps onto both x2 and x3, and so F is not did not start out as a one-to-one function. Okay, so this is the converse of f, and now we can re-express this as this is the domain of G, kind of small, but this is domain of G now. Okay, the ranges of f become the domain of the converse G. Okay, so instead of writing y1, we can now write x1, and instead of writing y2, we write x2, and then x3. Okay, and these arrows are not to draw any kind of mapping. There's no function in between here. I'm just simply saying we're reassigning the range to the domain of G. Okay, and now the domain of f becomes the range of G. And so instead of calling 1, 2, 3, and 4 x, we label them with a y. Okay, and you can see that G is not a function. Okay, G is a relation, and we can also say G is the converse of f, as we stated here. Okay, and here's an important bit of information that you may have already picked up on, and I may have mentioned it. The inverse function, and we label it with f with a superscript -1. The inverse function f of x exists if and only if f of x is 1-to-1. Okay, so what are our instructions for finding inverse functions? Well, first we check to determine whether the particular function is 1-to-1. Okay, we can use the horizontal line test. Then, if the function is defined by sets of ordered pairs, we swap out the inputs and outputs. Okay, so we would simply, for instance, if we had 1, 2, to write the converse, we would write 2, 1. Okay, and this would give us our ordered pairs for our input or our inverse function. Okay, so we could call this f of x, and this would be f inverse with the superscript of -1. Okay, what does C say? If the function is defined by an algebraic equation, okay, and we don't have ordered pairs, in other words, if it's expressed a different way, then what we can do is take the expression and swap or interchange the x and y and solve for y to get the algebraic expression for the inverse function. So example 4 wants us to find the inverse of each function. Okay, so I'm going to give these dots names. I've got 1, 2, 3, 4, 5, and I'm simply going to label them A, B, C, D, and E. Okay, and for the dots in the range of F, I'm going to label them 1, 2, 3, 4, and 5. Okay, so now I just want to swap the domain and the range. Okay, and so this this shape will now become our domain, and I will call the for now the converse of f G, and in the range of f I had 5 dots, so I'll put 5 dots here for the domain of G. Okay, and this is 1, 2, 3, 4, and 5. Okay, and I'll use an oval for the range of G, and I'll label them D, G, and R, G. And in the domain of F, I had A, B, C, D, E. Dot, 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 dot. Okay, so if I just simply reverse the arrows, A went to 1, and so I'm now going to draw an arrow from 1 to A. B in F went to 2, and so I return the arrow from 2 to B. And then C went to 3, and so 3 is going to go to C in G. 4 is going to go to D, and 5 is going to go to E. Okay, either way I go, each dot only has one arrow leading the way, whether I'm using F assignments or G assignments. Okay, so G is not just simply the converse of F, it is we will say G equals F inverse. Okay. B, again, we've labeled this F. Well, let's double check it and make sure it's a function. Our inputs are 2, 3, -1, and 4. None of the inputs repeat, so F is a function. F is a function. And to write the converse, and I'll call it G, we just simply start switching the input and output, the ordered pairs. So instead of 2, 1, I will have 1, 2. Instead of 3, 0, I will have 0, 3. The third ordered pair would now become 5, -1. And 4, 7 would become 7, 4. Now we look at G and we say, well, do any of these inputs repeat? 1, 0, 5, 7. None of the inputs for G repeat, so G is equal to F inverse. Okay, C, we have inputs for F 3, 2, 0, and 7. Okay, so let's reverse these ordered pairs and call it G. We have -2, 3. We have 1, 2. Okay, 0, -2 would now become -2, 0. And 7, 3 would become 3, 7. Okay, and these arrows aren't making assignments. I'm just showing what ordered pair we started with and what ordered pair it became for the converse. Now, G can only be called the converse of F, because if now you look at G, you see that we have two inputs that repeat. Here is a -2, and there is a -2. Okay, two inputs for G repeat. So G is not F inverse. Okay, F does not have an inverse function because F is not 1-to-1. Okay, what about D? Well, we have f of x is a linear function therefore it is 1, 2, 1. Well, how do we find f inverse? Well, we simply take the y and the x. Okay, here is what we were given for f, and now we want to swap the x and y, or another way to say it is for every place we see a y we put an x, and for every place we see an x we put a y. So I will call g of x equal 2y minus 1. Okay, in this piece I'm just simply giving it a different name. We don't know, well actually I do know that this will be a function because we started with f of x and it was 1 to 1, so I could go ahead and label this as f inverse. Okay, but we're mainly going to work with this piece and we're going to solve for the y. So if I added 1 to both sides, I would get x plus 1 equal 2y, and then if I divide by 2, I would find the expression for my inverse function, x plus 1 divided by 2. Okay, is f inverse. Okay, what about e? Alright, well, for e we have a function 2x minus 1. The square root of 2x minus 1 is 1 to 1, so we should be able to find the converse and it would end up being the inverse function. So I will label this as f inverse. I will swap the x and y. And now I'll solve for y. I start out by squaring both sides. This square removes the radical from the right. Okay, I'm going to have to make a little bit of room. And my next step to get y by itself would be to add 1 to both sides. So I'd have x squared plus 1 equal 2y. Okay, we simply moved the negative 1 over to the left and it became positive, and now I divide both sides by 2, and this leads to y equals x squared plus 1 over 2. Okay, and with this one, this is a function. Okay, so we can label it as f of negative 1 of x. Okay, we simply just have, there are, or in other words, the y has an odd exponent. Okay, we only have one equation or one expression that represents y. Finally, we have y equals x squared plus 3. Okay, and this is a function, but f of x is not 1 to 1. This is a parabola. Okay, and a parabola fails the horizontal line test. So I will call this g of x instead, and I'll do the same procedure. I will swap x and y, and so now the y is squared. I can start to try to get the y by itself. Okay, this gives me x minus 3 equals y squared, and now we run into the problem. I'll rewrite it first. And we have y squared, so we want to take the square root of both sides. Okay, the square root of a variable squared becomes absolute value of the variable, and now we have square root of x minus 3. Well, we could either plug in a positive square root of x minus 3 for y and complete the equation, or we could plug in a negative. And so what that says is that this results in two different expressions for y: a plus square root of x minus 3 and y equal a negative square root of x minus 3. Okay, this is not a function. For one input, we get two different outputs. Okay, so the inverse function for f in part E does not exist. Okay. Here we have a different situation. Yeah, we just said that a parabola is not one-to-one, and so it doesn't have an inverse function, but now we've restricted our inputs. Okay, so if I sketch f of x, okay, let me do one better. Instead of sketching it, I'll just use my calculator. Alright. Okay, I'll clear out the previous function, and I will put in here x squared minus 4, enter, and graph it. Okay, and the way it's pictured in the graph, it is not one-to-one. So we can't find an inverse function. We can find a converse, but the converse will not be the inverse function. Now, if we add in this little detail to the right, if we restrict the domain in that I simply ignore everything that is less than 0, and so basically what I do is I scribble out or erase this left half of the parabola. Okay, if I drop this left half of the parabola, then the rest of the curve will be one-to-one. I will no longer hit the curve twice with a horizontal line. Okay, so for part F, we are only considering this half of the curve. Okay. So for F, we will find an inverse function. So what we do is we say F inverse equals x. Okay, instead of writing y, I write x, and then I write y squared minus 4, and I go through the same steps I did with the previous problem. Different numbers. Okay, and now I take the square root of both sides, and I am going to get y equal plus or minus the square root of x plus 4. But now what I want to do, because obviously this is not a function, okay, I have to consider my domain. And as I stated previously with arrow diagrams, when we find the converse or the inverse, the domain of the original function becomes the range of the converse. So in other words, x has now become y, and so if I translate this inequality, I would have y is greater than or equal to 0. And so what that allows me to do when I consider this expression along with that inequality, I can rule out this minus sign. Okay, the fact that y is always positive knocks out the possibility that I have two equations. At this point, you may be curious about the x, okay, because this x was previously the y, and so we took the domain and it's become the range of f inverse. What did we start out with the range for f? Okay, let's look back at our calculator. Okay, here is our parabola, x squared minus 4. We ignored the left half. Okay, the minimum of x squared minus 4 is negative 4. And so the range of x squared minus 4 is negative 4 to infinity. Okay, what y values does this function cover? Okay, well, this negative 4 to infinity now becomes the domain of f inverse. So the domain of f inverse equals negative 4 to infinity. And if you look at the domain, it starts at negative 4. Okay, if we plug in a negative 4 into our f inverse function, we get negative 4 plus 4, 0, and the square root of 0 is a real number. And so any number greater than negative 4 will give us a positive number inside the radical, and so we're safe in that regard. Okay, so our f inverse is the square root of x plus 4. Okay, the second function, again, it's called f, and we have y equals 2x plus 3 over x minus 1. F of x is a function. If you have any doubts, we could take our calculator and plot it just to verify. Let's see, we will put in parentheses on the top, 2x plus 3 divided by x minus 1 graph. Okay, and so we see this has the rational function look to it. Okay, we have a horizontal asymptote passing through here, and then we have one vertical asymptote. Okay, but this is a function, and from the looks of it, it is 1-to-1, so we should be able to find the inverse function expression. Okay, so I will take this expression for f, y equals 2x plus 3, and x minus 1, And note that for the domain of f, x cannot equal positive 1. Okay, so now I am going to create my inverse function by swapping a y for x and x is for y's. So I will write 2y plus 3 and y minus 1 on the bottom. Okay, so I want to solve for y. If I multiply both sides of this equation by y minus 1, okay, so at this point on the left, what I can do is distribute my x, and I will have xy minus x and on the right I will have 2y plus 3. Okay, I will simply move my y variables to the left and this x to the right. So I'll say 2 minus 2y and minus 2y, and then I'll say plus x, and so now I have xy minus 2y on the left, and I have an x plus 3 on the right. At this point I can factor my y out of these two terms on the left, and I'll have an x minus 2 left and an x plus 3 on the right. And so now I can isolate my y by dividing both sides by an x minus 2, and this will give me y equal x minus 2 divided by x plus 3, and this is my inverse function. Okay. Theorem 2 states that the graph of a function f of x and the graph of its inverse function f negative 1x are symmetric with respect to the line y equal x. Okay, so in other words, if I take this graph of f of x and I rotate it around this dashed line, which represents y equal x, then I will graphically produce f inverse. Okay, so how do I do that? Well, one way, which is probably a pretty safe way to play it, is to pick points along the f curve and swap the coordinates of those points. Okay, so here we have negative 4, 0. Here we have 0, 2. There we have, I don't know, let's see, maybe I can call that 3, and this looks like it falls at y equal 5. And this one, I don't necessarily need to know the coordinates. It is on our axis of rotation, our axis of symmetry. So this point here is just simply going to stay put. So I will go ahead and make this red. Okay, f of x and f inverse are going to share this point. Now, 3, 5 for f inverse is going to become 5, 3. So I'll find 5 and I'll go up to 3 and plot a point. And so if I pass a line perpendicular through y equal x, okay, then what you should see is that this distance is equal to this distance. These 2 points, 3, 5 and 5, 3, are offset from y equal x perpendicularly from each other by equal amounts. Okay, so now I'll just continue with the rest of my coordinates. This point, 0, 2, will now become 2, 0. This point, negative 4, 0, will become 0, negative 4. Oh. Okay, and so I want to mirror this across the dashed line. So these 2 points share the straight section, and then from here I want to go up through this point that they share in common. Okay, and this this line has a little bit of a slant to it, so this really should slant off towards the right. This shouldn't be straight up and down, even though it looks that way. I just simply want to try to draw a sketch of f inverse. And now through these 2 points we see that f curves, and so likewise f inverse should curve through here and just mirror this curve with respect to y equal x. Okay, so to do this well, you have to be somewhat of an artist. I'm definitely not perfect at it, but as long as you get the idea. Okay, example 6, we want to sketch the graph of these one-to-one functions, and we want to sketch their inverses, and we'll just simply use what we learned on the previous page about y equal x as our line of symmetry. I'll use green. Y equal x is the identity function, so whatever we use for our x coordinate, we will simply have that same y coordinate. So it's really easy to plot. Okay, not so easy to draw a straight line. Alright, we're just simply going to rotate f of x around this green line. Okay, I will draw the square root of 2x minus 1 in black. Okay, let's see, where does this function start? Okay, let's figure out the domain real quick. 2x minus 1 should be greater than or equal to 0, so I add 1. Oh, not 0. I divide by 2. So this tells me x begins at 1/2. Okay, so I will start right about in here, and now let's see, I will plot some points for f of x equals square root of 2x minus 1. I have to be kind of picky here, because if I pick a bad number, then I'll get a decimal number, which is not always so fun to plot. If I say 2 times 2.5, I'll get a 5 and subtract 1, and I can take the square root of 4 easily. So f of, let's see, 2 1/2, I would get the square root of 2 times 2.5 minus 1, which is square root of 5 minus 1, square root of 4, and so I get a nice number for y. So at 2.5, which I'm going to say falls somewhere in here, I need to go up and plot y equal 2 right there. And the bigger I make my dot, the more room for error I have. Okay, and let's see if I can guess another good number. What if now I calculate, okay, if I say f of x, input 5, then I'll get the square root of 2 times 5 minus 1, which is 10, and then I get a perfect square inside my square root, which gives me another nice y coordinate, 3. So at 5, which is right about here, I can track my way up to 3, which is halfway between 2 and 4. I'm going to place it right there. Okay. And so now with my coordinates for f of x, this will be a lot easier to plot the inverse. Okay. So the coordinates for this were 2.5 and 2. This one had coordinates, let's see, 5 and 3. And this one down at the bottom had coordinates, let's see, 1.5 and 0. Alright, I can draw my curve for f of x. Okay, something like that. And now I just swap these out for my inverse function. Okay, I want to plot the point 0 and 1/2, 2 and 2.5, and 3 and 5. Okay, so whereas 3, it's right here on the x-axis, and I track my way up to 5, which is right about there. Okay. Alright, so you're probably thinking the same thing I'm thinking. These 2 points are supposed to be the same distance away from this green line, but keep in mind I did not draw this green line very well. Okay, so I'm just going to go ahead and try to put these points for f inverse in the right spots. Worry about the green line later. 2 and 2.5. Okay, x is 2, and I go up to 2.5. This is 3, and this green line is really starting to become a problem, so I'm just going to get it off for now. So 2 and 2.5 is going to land right about here. Okay, and now 0.5. I'm on the y-axis, and I land somewhere in here. Okay, so I'll redraw my green line. Not that we need it anymore, but it's going to shoot right down in between the middle of these points. Okay, so I'll sketch my red curve and just be done with this one. It will go up through the second point and then very steep up through the last one. Okay, so these curves should be mirror images, but this is the best I could draw them. Okay, so for g of x, and again we've restricted a domain. This is a parabola that starts at -4. I'll draw it in a different color. And now if I put in 1, I would get 1 squared minus 4 is a -3. So in between 0 and 2, I want to go down to right about there. And along the way, I'll label my points with coordinates. So this is 0, -4. This is 1, -3. What if I input 2? Well, 2 squared minus 4 would give me 0. So for g of x, I have my x-intercept. And I'll just go with these points that I have and just kind of extend it a little ways past x equal 2. Okay, remember it's half of a parabola, and I don't want to use any inputs, negative inputs for x, because we have this restriction here. X is greater than or equal to 0. X is positive. Okay. Again, I'll try to draw a decent y equal x curve. And then I have 4, 4. Okay, something like this. Alright. And I'll just go ahead and take this and extend it on past y equal x. And now I'll work on my inverse function. All I have to do is swap these coordinates, and so I am going to plot a point here for -4, 0. I will plot a point at -3 and 1. And then I'll have 0, 2. Looks like my y-axis has a slightly different scale. Okay, the right side of the x-axis is a little bit longer, even though it has the same units. So that's gonna cause our mirror of my inverse and my f of x to not really look like they're mirrored. Okay. And then this last point, let me label the coordinates 0, 2. And this one had the coordinates 2, 0. Alright. I'm ready to try to sketch my inverse function. Ooh. Okay. And I shouldn't be, that piece should not cut down like that if I want this to be accurate. But I did do one thing right up there here. The black curve passes through the green line right there, and so my inverse function should also. Okay, that's a little bit better. And maybe go back and try to trace over this to look a little smoother. And again, since my x-axis is longer than my y-axis with the same units, then these don't look very good in the way of a mirror image. Okay, the scales are different. Okay, but all I did was swap the coordinates, so I can be certain that this is an accurate curve for the f inverse. Okay. Our last theorem for this section, for a one-to-one function f of x, it says that if we compose the two functions, the f and its inverse, then we should get x. And if we compose them in the reverse order, then we get x as well. So in example 7, we're just simply going to put f into g and g into f and verify that we get x in both cases. So we're going to have to do a little simplification of algebraic expressions. If we place g of x inside of f, okay, f of x is a square root function, and we have a 2 times x, or the input. In this case, the input is going to be g of x. So instead of writing x, we put g of x inside, and f of x is 2 times x minus 6. Inserting the actual expression for g of x, we place a 1/2 x squared plus 3 inside. We distribute the 2, and the 6's cancel, and we get the square root of x squared, which is actually an absolute value of x. Okay, so we didn't get back x exactly. In other words, these are not inverse functions of each other. Okay, we want x exactly, not absolute value of an x. Okay, and if you just look at the graphs of both f and g, you'll see what the problem is. Okay, f is a square root function, and it looks pretty much like that. Okay, passes the horizontal line test. However, on the other hand, we have g of x is a parabola that is shifted up from the origin 3 units, a little more symmetric, but drawn this by hand. So g of x does not pass the horizontal line test. We strike g of x twice with a horizontal line. So g of x is not 1, 2, 1. So g of x can't have an inverse function. Now, if we restricted the domain for g of x to 0 to infinity, okay, written another way, you could write with a inequality. If we said g of x such that x is greater than or equal to 0, then that would strike out this part, this half of the curve, and then when we mirrored it about y equals x, we would get a curve that looked like this, and it would be identical to f of x, and we wouldn't mirror this left half. If I had mirrored the left half and we didn't have this condition x is greater than or equal to 0, then this red curve here, if I drew the whole thing in a solid line, this would not pass the vertical line test, which is an indication of a function. So in other words, if I draw a vertical line here, I strike it twice, and so that would not be a function. However, if, once again, I restrict my domain to only positive x values, that would remove the left half, and therefore when I mirror it through the axis of symmetry, I would only get this upper portion, and that would pass the vertical line test. Okay, but the way the problem stated, there are no restrictions on x. And so g of x is not 1 to 1. G of x, the original problem, is this full parabola. So there is no inverse function. F and g are not inverses of one another. Okay, so really we wouldn't even have to consider the composite of g and f. Okay, this could still work out to give us an x, but then the opposite order does not give us an x, it gives us an absolute value of x. So f and g are not inverses of each other.